In this lecture, we will discuss about the velocity potential equation and its application, and further we will initiate a discussion on finite waves. So, in the context of low speed flows or incompressible flows, we were talking about a velocity potential. We said that whenever there is irrotational flow, then there is a presence of a velocity potential, and often that potential is expressed in the form of gradient of a scalar. So, we had used the nomenclature grad small phi. So, in this case, when we are discussing it in the context of compressible flow, we are going to use a slightly different nomenclature to keep the two situations distinct from each other. So, here we will talk about velocity potential, but we will talk about it in the context of gradient of capital phi. So, of course, there is an irrotational flow that we are talking about now in a compressible flow field, and gradient of capital phi is going to help us bring in the perspective of velocity potential. So, keeping that in mind, let us first try to discuss where are the possible situations in a compressible flow field where we can have irrotationality, and in what other instances can we have a rotational flow field. So, let us start discussing by drawing a few sketches and showing some examples. So, this is a sharp wedge in a 2D situation or a cone in a 3D situation, which is immersed into a flow which is supersonic. Now, in due course we will study the aspect of shock waves, which are extremely strong pressure waves. These shock waves are formed when the flow is supersonic, and it is formed when an obstacle is put into a supersonic flow. Now, this happens to be a slender sharp obstacle, and the kind of shock wave that is formed can be represented like this. The shock wave is drawn in the form of two lines, and these lines are very thin regions across which large jumps in flow properties are produced. We will discuss about shock waves further in due course. So, we are just getting a very brief introduction to it, and remember that these are very strong pressure waves, while we talked about weak pressure waves earlier when we talked about sound. So, here if you look at the flow field upstream of the shock, you have an uniform flow field, and therefore, curl of the velocity vector is 0. Even downstream of the shock, with this kind of a shock wave, curl of the velocity is nearly 0. Of course, remember that here we are talking about an inviscid flow, and therefore, possibility of a boundary layer forming on this surface and creating a rotational flow is not part of the discussion. Let us look at some other geometries where this kind of flow can occur. We are now looking at a flow through a converging, diverging duct or nozzle. So, this portion is converging, area is reducing, the other portion is diverging where the area is increasing as we move along the length of the duct or the nozzle. Under suitable conditions, we have a subsonic flow here in the converging section, we have a sonic condition at the smallest cross sectional area and a supersonic condition in the diverging part of the nozzle. And again curl of the velocity is approximately 0. Let us draw another instance, again a slender object, but not necessarily a wedge. It could be a sharp ogive geometry, and this time the situation is slightly more difficult. You have a shock wave, but which is slightly curved, very slightly curved. As long as it is very slightly curved, curl of the velocity vector beyond the shock is still close to 0, but as it becomes more and more curved, the curl of the velocity vector will become unequal to 0. That means the flow will become rotational, which means curved shocks or strongly curved shocks produce rotationality behind them. Behind in the sense that rotationality is produced downstream of the shock. So, what makes the shock more curved? If you had made the obstacle more blunt, then this would have produced a highly curved shock. Of course, the shock will not be so close to the body. Let us redraw it. The shock will be thrown away some distance upstream of the body. So, this is what is called as a detached bow shock wave, which is highly curved, and the flow behind the shock is highly rotational. Remember that there is no boundary layer formation over here, it is still inviscid flow, but the flow becomes rotational, while upstream of the shock it was irrotational because it was uniform flow. In all these cases that we are citing, the flow is a uniform flow, and of course, it is supersonic flow. To express it as free stream, you can associate the subscript m infinity whenever we are talking about a free stream much ahead of the body. So, these are situations where you can distinguish between rotationality and irrotationality. We will cite one more situation which we have discussed earlier also, that is the boundary layer. Formation of a boundary layer over a certain surface. We have earlier discussed it in the context of incompressible flow. Similarly, in compressible flows, you can have a compressible boundary layer. The concepts remain quite similar, but you can expect realistic compressible boundary layers to be turbulent, and within the boundary layer, of course, the flow is rotational. However, beyond the edge of the boundary layer, it again becomes irrotation. Within a compressible boundary layer, you could also have strong temperature gradients, especially when the Mach number becomes large, a supersonic Mach number which is becoming larger. That would induce very strong temperature variations within the boundary layer. That's one reason for that is viscous dissipation within the boundary layer becoming much stronger, and also there could be shock related heating. Shocks become stronger as the Mach number increases. We will discuss these further in upcoming lectures. So, let us come back to velocity potential equation. So, we see that there is 3-dimensional velocity field in a compressible flow with Cartesian representation, and then we recall Euler equation which connects pressure and velocity changes in an inviscid compressible flow. So, we are recalling this equation which we have dealt with earlier. We are also recalling the irrotationality condition, that is the curl of the velocity equal to 0 for a 3-dimensional flow field, which means individually these components have to be equal to 0, only then the flow becomes irrotational. The moment it becomes irrotational, we use the identity that curl of grad of some scalar function, let us say phi, is equal to 0, and using that we introduce the gradient of capital phi for compressible flow. So, this is u, this is v, this is w for compressible flow. Let us invoke the steady form of continuity equation. So, that is divergence of rho v equal to 0. So, in differential form it is like this. Now, if you plug each of u, v and w in terms of derivative of capital phi into this expression, what do you get? You get this. Now, if you take those partial derivatives, what do you get? You get the second derivatives of phi, and then you get the remaining terms, where the first derivative of phi is multiplied by a corresponding first derivative in density. Let us move on. So, we will write the Euler equation in this form. We put the v dv term in this form dv square, and then we introduce the velocity components here to express capital V square, and thereby we can bring in the first derivatives of phi. We square them and we sum them and divide by 2. So, that gives you the expression here. We further know that the square of the speed of sound is given by del p del rho for isentropic conditions. So, we invoke that, and based on that, what can we write? We can write this equation in a form like this. Once we have that, we take a partial derivative with respect to x of this equation. So, that reflects here on the right hand side, and what does that give you? When you do the partial derivative with respect to x for each one of these terms, you get the corresponding terms here. So, that is the equation you get by taking a partial derivative with respect to x. Let us also take partial derivatives with respect to y. What you end up getting is here. with respect to z, what you end up getting is this. So, mind it that each one of these right hand side terms comprise of a first derivative and a second derivative in a product form, and you have to be careful about the indices. Finally, what do we get? We had this form earlier, and now we have obtained expressions for partial derivatives of density with respect to x, y and z separately in the previous slide. So, we just plug them in over here. Once you plug them in, you get this equation. It is a fairly long equation involving first or second derivatives of phi, but as you can understand that there are many terms where products of derivatives are involved, and that is going to give it a non-linear behavior. So, let us call this as a non-linear PD in phi and its derivatives. This equation is the famous velocity potential equation, and what is it combining? It is combining continuity, momentum and energy. So, everything is put into a single equation over here. Now, we are bringing in energy equation here by a means like this, that when you look at the energy equation in the context that we are dealing with, it basically gives you the statement that stagnation enthalpy is conserved. So, where from do we get it? So, we were discussing about that one dimensional flow for flow past a sound wave. So, if we were to look at a similar situation, a similar control volume and station 1 and 2 across the control volume. So, if you write down the energy equation across that control volume, for an irrotational flow field, you will see that if the flow is steady and adiabatic, then from your energy equation when applied to such a control volume, this is what comes out. I am leaving it as a homework problem for you to check. So, what does that say? It says that the summation of static enthalpy and the kinetic head, which comprises the stagnation enthalpy, that remains conserved. H naught 1 is the same as H naught 2, and therefore, H naught is constant. So, that is the statement made here. So, that is what we get from the energy equation. Now, for a calorically perfect gas, H naught is basically H plus V square by 2. So, we are representing H as C p times T, and then H naught as C p times T naught, and then replacing by gamma T by gamma minus 1 and gamma T naught by gamma minus 1. This is A square by gamma minus 1, the other is A naught square gamma minus 1. So, A square is the sonic speed based on the static temperature, A naught square is the sonic speed square based on the stagnation temperature. Now, putting the expression u square plus v square plus w square to represent the capital V square, we can now bring in the first derivatives of phi to replace the small u v w. And therefore, you now have an equation for A square. What does it say? That it is not going to be A naught square everywhere, it is going to be dependent on the UVWs which are existing locally in the flow field. Accordingly, A will change from one point to the other in the flow field. So, it will have spatial variation. So, there is no analytical solution available for the velocity potential equation, where the A square term is defined by the second equation here. However, you can solve it numerically by applying suitable boundary conditions and obtain the phi field. So, once you obtain the phi field by taking the spatial derivatives, the first derivatives, you can obtain the u's, v's, w's, etc. And then you can also calculate the pressure variations in the flow field by using the Euler equation. Now, note that the velocity potential equation is a nonlinear partial differential equation, which we already talked about, and it has to be solved simultaneously with the sonic speed equation, because A square is seen in each and every term practically of the velocity potential equation, and it basically comes from this equation, and it is applied to any irrotational isentropic flow for all ranges of Mach numbers. So, it is not confined to any specific Mach number, you can apply it to subsonic, transonic, supersonic or hypersonic ranges. But you have to be careful whether under a particular flow situation the irrotationality and isentropic nature of the flow field is at stake. So, accordingly, it has to be applied only to irrotational and isentropic situations alone. Well, if you were to apply it to an incompressible flow situation where A tends to infinity, then what you get back from there is the familiar Laplace equation, which we have discussed in earlier lectures. So, basically when you substitute A tending to infinity, most of these terms will cancel out. What will be left is only the terms involving the ones over here. The rest of the terms will all vanish, and therefore, you get back the sum of the second derivatives, spatial derivatives in phi, which is Laplacian capital phi equal to 0. So, this is a bit of an introduction to velocity potential equation. Let us move on, and we will initiate a discussion on finite or nonlinear waves involving waves of both expansion and compression kind. So, earlier we were discussing about weak waves. Through the example of sound wave, where we talked about very small changes in the flow field when the sound wave passed through. So, there was a very small change in the speed of sound, in density, in pressure and so on. And now, on the other hand, if the wave becomes a strong wave, then we can expect that these values, the changes, would no longer be differential, but they could become finite changes. Let us say there is a detonation, there is an explosion. So, that produces a strong pressure wave, and that can be called as a finite wave. A finite wave can be of an expansion or compression kind. Let us try to develop further on this concept. So, for that we will keep referring back to the sound waves once in a while. So, when discussing about sound waves, we need to recall a few features. If you were to represent the passage of a sound wave in the form of a small ripple which is propagating through the x t plane, where x is the physical location of the weak wave and t is the time over which you are observing the wave, then you will find that with passage of time this wave would propagate through the domain and it will be translated to some other location between the time t equal to 0 to some other time t equal to t 1. And the wave form remains unaltered and you can represent the propagation of that waveform by stating that the dx dt is equal to a. That is the sonic speed. In the case of finite waves, as we said, larger changes are produced so the delta rho, delta p etcetera are larger, and now further the local velocity of the flow comes into the picture. When we look at propagation of finite waves. What do we mean by that? We were talking about looking at the wave propagation in the x t plane. So, when we look at finite waves, a wave which is moving towards the x direction may be curved, because along that wave the equation that you have is dx dt is equal to u plus a. That means, the wave is strong enough to also alter and influence the flow velocity. Additionally, the wave form gets altered over time as it propagates through the domain. These lines along which dx dt is a defined quantity, like it is dx dt equal to a in the case of sound waves, are called as characteristic lines. This is a right running characteristic for a sound wave. This is again a right running characteristic for a finite wave. The only difference is that in this case the u is coming into the picture. If there were left running waves in the case of sound wave, they would propagate like this. with the characteristics remaining straight lines, and they all have the same slope. While in the case of finite waves, different portions of the flow field can have different characteristic line slopes, because of the same reason, that because u plus a is involved and u is a function of space and time, therefore, the dx dt will be a function of space and time, and again they can have left and right running types. Characteristics of two opposite families can intersect, but characteristics of the same family cannot. So, you can have a right running characteristic and a left running characteristics meeting and crossing over, but you cannot allow two right running characteristics to cross each other. That would lead to violation of the second law of thermodynamics. Finite waves, as we said, can lead to expansion and compression. When does that happen? If the characteristic waves are like this, that they are moving further apart in the xt plane, then we have an expansion. If on the other hand, the characteristic lines are tending to get close to each other, then we have a situation of compression. In this case, in the case of expansion, the characteristics are moving further apart, because the dx dt equal to u1 plus a here is larger than the u2 plus a here, still larger than the u3 plus a here, but here it is just the other way around. So, this has a small velocity, because the dx dt is basically talking about velocity. This has a large velocity. So, larger velocity characteristics are tending to catch up with the slower one, and they are trying to come and cross each other. Now, the crossing is going to violate entropy conditions of second law. So, what they can do is they can merge with each other and form a final wave, which is much stronger in nature than the constituent characteristics, and this is how a shock wave is formed when the characteristics are getting closer. This produces compression of finite waves, this produces expansion. We will later see that compression of finite waves lead to shocks, which could be of the normal or oblique kind, while when it is expansion, they produce what is called as an expansion fan. So, that was a brief description of the nature of finite or nonlinear waves, which could be of the expansion or compression kind, concept of characteristics, and formation of shocks from finite compression waves. So, in this lecture we discussed about the velocity potential equation and its application. Subsequently, we initiated the discussion on finite waves and concept of characteristics, and briefly talked about expansion waves and shock waves, which we will discuss with further detail in the upcoming lectures. Thank you.